I started recording, and now let me share the screen. Good. Okay, so now I shouldn't have any more commitment, and our lectures should move forward smoothly. So let's stick on the calendar, which is on the website. And May 6, subscriptions to the exams will open. Nothing new to tell you here. And so let's move forward with the estimation of climate impacts. And we are now focusing, as you may remember, on rainfall runoff modeling as a means to get an example of how the climatic input can be translated into the output that we wish in terms of impact on the system that we are analyzing. In this case, the system is water cycle, and therefore we are trying to estimate how the climatic input, whatever it is translated into, in this specific case, river flow. I want to conclude the treatment of the linear reservoir, the discussion on the linear reservoir, and then I will make some considerations, some final consideration on this type of approach. So using a model to decipher, to understand the impact of climate on the system that it's under exam. So last time we got the final expression of the linear reservoir, which is on the screen here. Okay. And finally, as you see here, I cannot select the analytical relationships, but the final expression is this one. And there is an integral because I told you that the motivation for the integral being still there is that we don't have an analytic expression for precipitation. Precipitation depending on time tau in this case. So had we had analytical expression for precipitation to plug in into this formula, we could try to make an analytical computation of the integral, which is not particularly a complicated integral. The integral is a summation, actually, and therefore, I mean, given the current availability of computing resources that everyone has at home, it's not necessarily to be computed because we can substitute the integral with the summation. And this is a linear model because it's a linear expression. It's a linear relationship relating the river flow Qt to precipitation P tau in this case. And so, as I said, it's just a summation, and you can substitute the integral with a discrete approximation. It's easy. We will do that. We have an exercise. And you will see that I hope that we have time to make this exercise, but I would say yes. And you will see that it's extremely easy. On the other hand, let's take into account that if you have a means to compute the integral analytically, it's always preferable because there is a reduction of uncertainty. Because, as you know, numerical integration implies the introduction of a numerical approximation, which is another source of uncertainty, which sums up to the other uncertainties that are called into play anytime that we apply an environmental model. So when it's possible, I mean, we shouldn't refuse from the attempt of analytical integration. In this case, we can easily compute the integral if we assume that precipitation is constant. Of course, this assumption is not really reliable. You understand, precipitation is never constant. It's varying every second. Rainfall that falls over a given location, and in this case, rainfall that falls over the catchment, it's never constant. But of course, if you refer to short time windows, you can assume that it's constant. And in any case, it is interesting, in order to understand how the model works, to see what happens if rainfall was constant. It's interesting and I would say educational. It's instructive because it helps you to get how the model works. And as we said several times, it's extremely important when you use a model to get a preliminary idea of the results, a preliminary expectation, because this expectation allows you to make a check of the reliability of what you computed. And in order to elaborate this expectation, you have to understand how the model works. So you should never apply a model without getting a preliminary understanding of what kind of model is and what you are expecting. In this case, it is relatively simple because the model is linear. So it's a transformation of rainfall into runoff. And of course, you have to expect, being the model linear, that when you have higher rainfall, higher runoff, and when you have a sudden jump in rainfall, you may expect a sudden jump in runoff. Of course, with some transformation operated by the model, but it is relatively easy to gain this expectation. But let's assume that rainfall is constant, okay? So P is a constant, doesn't depend on time. And then let's try to compute the integral. If rainfall is a constant, you can bring rainfall out of the integral because you know that any constant can be brought out of derivatives integrals, and therefore you get this expression here, and where rainfall is out of the integral, and the integral is particularly easy to be computed. And this is also the reason why we like this model, and better to say, people, when it was introduced about 100 years ago, liked it because the integral is relatively easy. So let's look at the screen without moving to the blackboard in this case. And then you see the integral of e to the power of something is, first of all, let's look at the content of the integral, okay? It's e to the power of minus t minus tau divided by k, okay? Remember, t is not variable. T here is the upper extreme of the integration. It is fixed. It is the time at which I want to compute the river flow. It is fixed. So the e to the power of minus t over k can be brought out from the integral because it's a constant. T is fixed. It's tau that is varying. Okay? So this is why in the second step here, you see that e to the power of minus t over k is out of the integral sign. You can bring it out. And therefore, inside the integral, you get left only e to the power of tau over k. Look at the previous step, minus minus give a plus. And therefore, what remains inside the integral is just e to the power of tau over k in the tau, which is extremely simple to be computed because it is the integral of e to the power of something is e to the power of something, okay? And therefore, the integral, which is computed in this third step here, is just e to the power of tau over k multiplied by k because it's the derivative of the exponent, okay? So it's the integral of the exponent, actually, which you have to bring here, and then the limit of integration between 0 and t. Okay? And therefore, if you compute the argument inside the square parentheses at the extremes t and 0, you get what you see here. And here there is a round parenthesis, a right parenthesis that is left there, shouldn't be there. I will correct it. So forget this right parenthesis. Of course, it shouldn't be there. And therefore, the result of the integration is what you see here. K to the power of k multiplying e to the power of t over k, which is what was inside the previous step into the square parenthesis computed for the upper extreme of integration. And then I have to substitute here 0 instead of tau. And then e to the power of 0 is 1. What remains is just k with the minus sign because, of course, I have to subtract the computation at time 0. So this is the result. And then you can rearrange everything in the final expression here. Qt is equal to precipitation, which is constant, which multiplies 1 minus e to the power of minus t over k. Okay, this is the final result, which was obtained by the previous step by just rearranging the right-hand side. Okay. Now, what is resulting here? What you see in this picture. So for progressing time, I can compute river flows for increasing t. Okay, as t increases, the second term inside the square parenthesis goes to 0. Okay, because e to the power of minus t for increasing t goes to 0. Okay, and therefore, for increasing t, the river flow is tending to precipitation asymptotically, because the term e to the power of minus t over k is asymptotically going to 0. So here you have asymptotically that river flow converges to rainfall. Remember that it's a rainfall multiplied by the area of the basin. So the units are consistent. The units of precipitation and river flow are consistent. So again, asymptotically, river flow converges to precipitation. And the speed of convergence is regulated by k. If k is large, you have a slow convergence. If k is small, you have a fast convergence. Okay. And of course, given that the curve starts to 0 and converges asymptotically to rainfall, the concavity of the curve is headed towards the bottom of the graph. Concavity is downward, down looking, okay? Now, consideration, here we are starting from 0, precipitation 0, river flow 0. Why? We are starting from the origin here because we assumed earlier, I go up, okay, to show you the assumption. We assumed earlier that Q0 is 0, okay? So the river flow at time 0 is 0. And this is why we start from the origin here. You can try, it is very easy to remove the assumption. So I go up again. It's very easy here. You have a term Q0 above here. Look at my mouse. It is very easy to remove this assumption. We don't do that. For your curiosity, you may try because it's very easy to see what happens. What happens is that you obtain a result such as the graph doesn't start from the origin, but starts from the value of Q0. It is very easy. Once again. Okay, so this is the result. Now, some practical, very empirical consideration. What you see here is reasonable because actually it is what happens that if you have a constant rainfall, river flow at the beginning is not responding to rainfall. as rain starts, you don't see any river flow. But if rain continues, you start seeing river flow, and the river flow keeps increasing, is increasing. And why at the beginning you have river flow 0? Because the basin, the catchment, it is storing the water. It's absorbing rainfall. It doesn't deliver rainfall immediately to the river. The catchment, it's like a sponge. It absorbs rainfall, and you don't see any river flow. And this is the effect of the linear reservoir, indeed, of the reservoir effect. The catchment is storing water, and you don't see any river flow. But if rainfall continues, then you understand the catchment gets saturated. And when the catchment is saturated, any more rainfall, any subsequent rainfall, immediately generates a river flow of the same amount of rainfall, because the catchment doesn't absorb anymore, doesn't make any storage anymore, and this happens asymptotically, coherently with this model. So indeed, it is what we expect, that if rainfall continues, at the end of the story, we get a river flow that is equivalent to rainfall asymptotically. And this is a condition that, of course, we don't like, because we like instead the filtering effect, the mitigating effect of the catchment that is storing water. Now, about the role of K, we said the larger the K and the slower the convergence. What is K? Remember the equation. Now I go to the blackboard. Just 1 second. I change the camera and let's put it here. Okay, good. Now, what we said, one of the assumptions of the linear reservoir is that QT is equal to WT divided by K, or equivalently the same, WT is equal to K multiplying QT. Okay, so what can you see here? You see from this equation that the larger the K, the larger the storage. So for the same value of river flow, the larger the K, the larger the storage, which means that the catchment stores more water. So the larger the K, the larger is this mechanism of absorbing water, which mitigates the river flow. And so this is why we should indeed expect that if we show here Q, T, and here time, and this is P, this is P, the larger the K, the slower the convergence. So this is large K, and this is a small k. This is small k. This is perfect, I mean, because it reflects what's written here. And you can make an experiment. When we will apply this, this model, you can change the k value and see how the graph changes. It is very easy. Once that you have the code into R or Python, let's say R for now, because we didn't explore Python much yet, you see this effect, which is fully understandable, and also tells you that, 1 second, tells you that what is the k value that you may expect for a catchment depending on the catchment conditions. So if you have a catchment that is impervious, very rocky, and just a small amount of the catchment covered by soil, you don't expect my and you don't expect a large storage. If the catchment is very steep, rocky and steep, you don't expect a large storage, and therefore you have to expect that K is small. If you have instead a very large catchment with a lot of lowlands covered by soil and the catchment is not steep, you may expect a large K value, which means a slower convergence to the most critical situation, because when river flow reaches rainfall, precipitation, it's critical. It's very critical because it means that any filtering effect, any mitigating effect of the catchment is gone. So this is why for the Po River, you have the convergence for very long rainfall. So the Po River is put in a critical situation for very long-term rainfall. So you have to get a very long rainfall before getting to a critical situation where the storage is depleted. There is no more storage. For small basins, steep, rocky basins, unfortunately, even a short rainfall puts the catchment in a critical situation because the storage is depleted very quickly. All of these discussions helps you to gain this expectation, which I was mentioning before, expectation of the final result that allows you to say, yes, this is what I was expecting. This is a good model, which is particularly important when you work in practice, because I mean, if you make a mistake in writing a scientific paper, okay, it's a scientific mistake. It's not good for your career, but it's a paper. If you make a mistake when designing a dam or a bridge, you understand the difference, okay? It's still your career in a worse way with respect to a scientific paper, and it's also the life of people, and it's at least economic resources that are gone if you make a mistake. So especially when you work operationally, it's extremely important that you understand what you're doing. It is a paradox because you may expect that it is more a need for the scientist to understand what's going on. Actually, I would say that it's a paradox. It is paradoxically, it's more needed for the technician to understand what's going on than for a scientist, which is, I mean, it's the scope of the science to understand, but it is a paradox, and that, the scientist, if makes a mistake, it's less, I mean, the impact is less relevant. Okay, so one more thing I want to say. If you remember, we started from a conceptual sketch of the linear reservoir. We sketched the catchment as a tank with a bottom discharge. I want to remake it here. We did something like this. Okay, and we said this is the storage, WT, this is precipitation, PT, and this is river flow, QT. We started from here, and there was one thing that I told you. I said storage assumed to be unlimited. So this is not a contradiction. It's not a contradiction with the fact that I just mentioned the case here where the catchment is reaching the upper value of the storage. Okay, of course, the catchment has an upper value, and the upper value is reached, as I said, with very long precipitation. Actually, the same happens in the model, because when you get to a situation where precipitation is almost equivalent to river flow, so there is only a slight difference, the storage is not increasing anymore. So even if we assume that it's unlimited, in practice, when you apply the model, depending on the value of K, you reach a situation where the storage keeps increasing because it's asymptotically. The equivalence between precipitation and river flow is asymptotic. So the storage keeps increasing, but in a very small manner after a certain time. So in practice, it is a reasonable approximation that you reach a value of storage, even in this model, which becomes almost constant from that time on. So it's not a contradiction. I mean, of course, this is an assumption that, strictly speaking, is not verified in the catchment, because in the catchment there is an upper value. But on the other hand, even according to this assumption, there is almost an upper value, because there is a value that is reached asymptotically. And therefore, it's, of course, an assumption that is not fully equivalent to reality, but it is mimicking in a reasonable way, in a reliable way, what is happening in the reality. So basically, what happens is that if you have a low K, you have less storage, so you reach very quickly a situation where the storage, even if unlimited, doesn't increase quickly after a small time if K is low. It keeps increasing, but the increases are very, very tiny, very, very small. So it is a reasonable assumption. If K is large, then the storage gets a longer time in order to reach its maximum. And then the final value of storage, the resulting value of storage, is much larger. Good. Now, you may remember that when we introduced the rational formula, we introduced the concept of concentration, time of concentration, which is the time taken by the drop that falls in the most remote point of the catchment, the time that that drop takes to reach the outlet, to reach the river flow cross section we are interested in. Okay, it is a measure of the response time of the catchment, the time that the catchment takes before responding to rainfall. You may see an analogy with what I said today. I said, if K is small, then the catchment responds quickly. There is less storage, and therefore the curve that you see on the screen goes very quickly to the asymptotic value. Conversely, I said, if K is large, remember, K is a time, the unit of K, you can see from the equations that I previously written here, it's a time. For larger K, it takes a long time to the catchment to respond. So you see an analogy between K and the time of concentration. Indeed, this is recognized by the literature. And under certain assumption that we don't discuss here, the literature says that K is more or less equivalent to 70% of the time of concentration. Again, under certain assumptions that we don't discuss here, the literature says that K is more or less, this is a rule of thumb, 70% of the time of concentration. This is very useful, because to apply this model, we need to know K. Otherwise, if we don't know K, if we leave the symbol K there, we cannot make any computation. We need to put a number there. And this number is representative of a time, because K is a time. Good. Now, how to guess this time? This is, for a modeler, K is a parameter. For a modeler, this is a critical question: how to fix parameter values. So this indication that I just gave, it's very useful, because you can get a guess value of K. But there is a but. The concept of time of concentration, it's a concept that it's a fuzzy concept. How to estimate the time of concentration of a catchment? There are several empirical formulas, but it is well known that these are highly uncertain, because you understand, starting from the definition, the time taken by the drop that falls in the most remote location of the catchment to reach the outlet. You understand that how can this time be computed? The drop first moves along an hill slope or inside a hill, and then the drop gets to the river, but the river is first steep and then the slope goes down. So it is a concept that can be understood easily, but can be the time of concentration cannot be quantified actually. So this useful indication that K is more or less 70% of the time of concentration, it's useful, it's very useful, but unfortunately we don't have a way, a quantitative way for estimating the time of concentration. So the question is still open, but still the rule of thumb is valid because you understand the Po River, the time of concentration, what is a guess? We know that the Po River takes a week at least after a precipitation, before getting a flood. So we understand that the time of concentration of the Po River is of the order of at least 1 week. If we talk about a urban catchment, so you get an extreme rainfall during summer in Bologna. How long it takes before the sewer system is affected critically? Few minutes, like 5 minutes. After 5 minutes, you may see water along the street because the sewer system doesn't take water anymore, which means that the time of concentration of a urban catchment is few minutes. So, I mean, the indication is useful because you understand the difference, at least the physical difference. Still, the question remains open of what is the precise value of K that I have to plug in here. And this is what we discuss in the next lecture, the next link. But before discussing this critical question, how to estimate model parameters, remember, in the rational formula, again, you had a critical parameter to estimate, the runoff coefficient C. It's critical how to estimate the runoff coefficient. Still, it's a question. And moreover, in the rational formula, there is another parameter, is the duration of rainfall that I plug into the rational formula. So it's a relevant question, how to prepare a model for application. After you decided, I use the linear reservoir, okay, critical question, how to estimate K and how to find rainfall data to plug into the linear reservoir, because I can get observed data. This is relatively easy, but remember, you need rainfall over the catchment is not in a single location. In fact, this is one of the things that is discussed here, and somewhere in the web page, you will find the concept of area rainfall, how to compute the rainfall over an extended area, starting from a measurement, which is a point measurement usually, because we measure rainfall by, as I said, by putting a tank outside and measuring rainfall. We measure rainfall in a point in space. So how to estimate rainfall over the catchment? These are still open questions. The literature gives a lot of information. We don't discuss everything. But we will see an application, and therefore we will discuss some specific questions. But before we turn into the discussion of preparing the model for application, let me mention just briefly, no analytical computation, other type of models that we can use, starting from the nonlinear reservoir. And, let me show you this sketch. This is an example. It's the counterexample of, this is the sketch of the linear reservoir. What you see on the screen is a sketch of a nonlinear reservoir. And basically, this reservoir becomes more complicated. First of all, you see that it's the shape, the geometric shape, it's like a V, and which means that you may have storage increase that is very fast at the beginning and then becomes, so K may be changing in time, K not constant, okay? And you may have, instead of a bottom discharge, you may have a discharge that is located not in correspondence of the bottom, which means that you wait some time after rainfall starts before activating the river, let me use this term, before seeing some river flow in the river. And you may have more than one discharge. All of these changes introduce nonlinearity. So if you introduce a K that is varying with time, it's nonlinearity. If you put a discharge not in correspondence of the bottom, it's nonlinearity. You can understand easily why. Because these discharges, when they get activated, if they are not activated from the time zero, when they get activated, they are thresholds. And thresholds mean nonlinearity. In fact, one of the problems of these schemes is that the shape of the hydrograph may be characterized by some steps, like sudden increases of river flow under given conditions. These sudden increases are the expression of nonlinearity. They can be there. It happens. It happens that catchments are characterized by threshold effects. It may happen. And you understand that writing the equations for this kind of nonlinear model is not difficult. I mean, in the same way, I wrote the starting equation of the linear reservoir, Pt minus Qt equal to dWt in dt. In the same easy way, I can fix the values of these thresholds, location of the discharge. I can allow very easily K changing over time, assuming different values, depending, for instance, on storage. It is very easy to write the differential equations. So to write the equations in differential form, it's very easy. Analytical integration probably would not be possible anymore, because when you have these nonlinearities, you are forced to use the numerical integration, which is, I mean, can be done. It's not a problem. The only thing is that you probably have to introduce more than one parameter. The linear reservoir has this nice feature, just one parameter, K. Here, you have the position of the discharges, and so it means the positions are parameters. The levels at which these discharges are activated. And then if you have different K values for any discharge, it's a parameter. Fourth. So, I mean, even if writing the differential equations is easy, is as easy as for the linear reservoir, actually application becomes not so easy, because of the need of estimating more parameters. Remember, the more the parameters, the more the complexity, and the higher the uncertainty. Increasing number of parameters means that the model is more complex, and complexity means uncertainty. Another consideration, complexity means, in most of the cases, a more reliable representation of reality. Reality is complex. So if you want to get with high fidelity a representation of reality, reality is complex, and therefore you need a complex model. But the complex model is more complicated to apply, and it's more uncertain. And therefore you understand with your intuition that if there is more uncertainty, you need more information. If you want to mitigate uncertainty, we said that we need more information, we need more data. And so this is why sometimes you may listen experts saying this is a too complicated model for the information that we have. Because if you use a complicated model with limited information, you get a lot of uncertainty. And these are all concepts that you should really assimilate. Okay, reality is complex. We need a complex model, but on the other hand, a complex model entails more computational effort, higher uncertainty, and in turn, complex model means need for more information. And these are questions that are extremely actual today, because on the one hand, we have an increasing amount of information. Now we have satellites that are seeing everything. So think at, for instance, at Google Earth. Google Earth is relatively young. It is, I mean, maybe it has been introduced 15 years ago, but the current use of Google Earth, it's much younger. It became accessible like 10 years ago. And I mean, it's a massive amount of information that allows you, in certain cases, to avoid, at least in part, the need of being there and see what's going on, because you can use Google Earth to see the shapes of the catchment. And I mean, it's really relevant. It's really relevant. And it is open, it is freely accessible. And it is not yet largely used for scientific research, or, okay, scientific research, people are starting using it. But for practical applications, this information is still poorly used. And it is a relevant question how to manage this information, how to profit from this information that is available. It's still an open question, and this is why the discussion on information model complexity is actual. And you may have heard experts talking of digital twins of the Earth system. This is a terminology that became popular 3 years ago, not more than that. And the idea is to make a numerical replicate of the reality. Of course, you need a very complex model, but now we have a lot of information that may allow this. So the digital twin is still a dream, but it's a dream that is materializing, and there are several research projects dealing with that. Also for the prevention of hydrological disasters, of landslides, of floods, droughts, people are exploring the value of these digital twins that may allow us to make predictions and to test policies, to test the outcome from different hypotheses of water resources management, river basin management, etc. And of course, a rainfall runoff model is let's say, a rough example of a digital twin. Also, the rainfall runoff model is mimicking reality, but the models that we mentioned and we studied, the rational formula, linear reservoir, are rough approximations. So I wouldn't call them really digital twins, but these are the ancestors of what we mean today for a digital twin. And of course, if you use a more complicated model, rainfall runoff, and then you couple the rainfall runoff model with an atmospheric model that should reproduce precipitation, and then you couple the rainfall runoff model with a groundwater model that should simulate groundwater flow, because also groundwater contribution to floods and droughts is extremely important. To droughts, of course, because when we get a drought, you know, surface water resources get depleted soon, and then we have to resort to using groundwater. And therefore, we need a groundwater model. But also the groundwater contribution to floods is important. And therefore, you need to couple all of these models, so you get up with a monster with millions of parameters, which is the digital twin. And then you have to manage the information to use it. So this is where science is heading to. And from a technical point of view, still, in most of the cases, we use a linear reservoir. So to study, I am doing some computations on the flood in the Romagna region 1 year ago. And for the case of that flood, especially for the flood from the small lowland canals, still we use the linear reservoir because it provides good approximation. Okay, so I think we are done here, and there is here a short discussion and to estimation of future forcing, because of course, if you want to run these models into the future, we need future rainfall, and therefore we fall back on the case of climate models that are supposed to be used for generating climate scenarios, but it's a discussion that it's I'm just mentioning here, and we have already discussed in other cases uncertainty of climate models, how climate models are structured, and etc. Okay, so with this lecture, I think we are done. Any question? And then I think we can pass to model calibration and validation. A question. Yes, please.
Can you explain the concept of the reservoir that has an upper value also in the model?
Okay, good. Good. Let me just go here to this graph. Okay, this is a graph of QT. This is the graph of QT depending on time. So let me just delete the sketch of the linear reservoir here. I think you can easily remember it. Okay. So what is instead important to that I write here is the relationship. Let me write it again. The relationship between WT and QT. So WT, remember, is given by a constant that multiplies QT. So I can easily transform this graph into a graph that shows the progress of WT depending on time, and it is a similar progress. It asymptotically tends to a limiting value. Okay, and so what is this limiting value? It is let's call it W star. It's equal to K and K for PT. So if you assume constant rainfall, and this is, let me remove the dependence on time. If you assume constant rainfall, you have a limiting value which is reached asymptotically for the storage, which means that actually even if we don't put an upper value for the storage in the tank, actually once that we fix the rainfall, according to this model, we fix an upper value of storage. Okay, this doesn't mean that we fix an upper value of the storage into the catchment, because in this case of the model, if I increase rainfall, I increase the upper value of the storage. This doesn't happen in the catchment. The catchment has a physical upper value of storage. It's like a tank with a given capacity. So the catchment, independent of rainfall, when it reaches, has an upper value of storage. When it is reached, it's reached. In this model, actually, you don't fix an upper value, but in reality, given that we deal with an observed rainfall that in this case we assume to be constant, we get very close to it, because we get very close to this kind of representation. It is not the same, and it is not the same because we should put if we want to reach the same situation, we should put an upper value to the storage. So to say, once that the upper value of the storage is reached, it's like a threshold, then any rainfall is transformed into runoff. It's like a threshold, but the reservoir wouldn't be linear in that case. So we accept the approximation that there is not a physical upper value, there is an asymptotic value that is reached, but depends on rainfall. I'm not sure if I was clear. Good. Other questions? Okay, now I anticipated that a big question is indeed validation, sorry, not validation, parameter estimation. Okay, parameter estimation, we have a term to indicate parameter estimation, several synonyms. Parameter estimation can be called parameter estimation, can be called parameterization, can be called optimization, model optimization, can be called calibration, model calibration. So parameter estimation, optimization, parameterization, calibration is the same thing. In hydrology, usually we use calibration. I don't know why, okay? And in the climate literature, you don't find calibration. They don't like it because they don't like it, and they use something like parameter estimation, parameterization, thing like that. Why they don't like calibration and hydrologists? I said, I don't know. Hydrologists use it. I don't know actually, but I have an interpretation. I think calibration means that implicitly means that the model gets a good representation of reality. Calibration means that I am adjusting to mimic something, okay, to emulate something, which is what we do in hydrology. When we talk about river flow estimation, we use model for really getting a reproduction of what is going to happen or what happened, but a technical reproduction. In climate science, models are not meant to, strictly speaking, to provide a technical indication. They are not meant to reproduce something that has been observed or something that may happen. They aim, this model, to understanding climate change. This is the main purpose of climate models and climate science. The purpose is understanding climate change. So they don't like any comparison of the model with what happened or what may in reality happen. They don't like it. And they don't like it because the purpose of the model, as I said, it's not to reproduce an event or to simulate an event. The purpose of the model is to understand climate change, to understand how the climate emissions, mitigation of climate emissions can lead to a mitigation of climate change. And therefore, they don't like calibration, the term calibration. But for our purpose, let's just take into account that you may read calibration. It means parameterization. It means optimization of the model. It's the same thing, okay? Validation is a different story, and I will tell you later what is the difference between parameter estimation and validating a model. You can already get some preliminary intuition of what validation means with respect to calibration, but we will discuss it later. So, how parameters of a model are estimated? There are, in view of the premise that I just made, that different disciplines attribute to parameter estimation a different purpose, then it follows that, of course, there might be different procedures for parameter estimation. 1 second, it's opening. Okay, here we are. Okay, and look at this graph that is taken from Wikipedia, I think. And let me open in another page. This is an hydrograph. I'm sorry, it's not very clear, but you can understand what it means. This is an hydrograph. Hydrograph is a graph of the river flow against time, river flow, river discharge, they are synonym, against time. And you see here that there is observed and simulated, okay? The thick line, the thick red line is observations, and the dashed line with the points is the simulation. Perfect. So you understand that here there is a comparison between observed and simulated, precisely the thing that I said, it's not the purpose of climate science. It's the purpose of meteorology, yes, but not climate prediction. So this is the way in hydrology, and you understand hydrology also because you see that in hydrology it's river flow, so it's clearly related to hydrology. This is how in hydrology usually a model is parameterized. Parameters are estimated. We compare observations with simulations, and once that we are happy with it, we say, okay, this is the value I want of the parameters. And the comparison in ancient times was visual, like here. So I look at this graph and I say, I am happy. Okay, I see that the model anticipates a little bit the peak, but if I'm interested in the estimation of the magnitude of the peak flow and not the timing, I mean, this is perfect. The magnitude is very well reproduced. Remember that in hydrology, I mentioned to you uncertainty is in the order of, if it is 20%, we are fully happy. So, I mean, this mistake, this error in reproducing the peak flow is much less than that, maybe 1%, maybe, and maybe lower. So that's fine. And the timing is not perfect because probably there is an anticipation of a couple of hours, which, I mean, can be a huge difference depending on the purpose of your prediction. But if the purpose of your prediction is just the reproduction of the river flow, this is perfect. Of the peak, I mean, of the peak. This is perfect. So the visual comparison, they start from that, as I said, looks at what you are interested in. So if you're interested in the reproduction of the peak, as I said, perfect. If you are interested in the reproduction of the time to peak, timing, you would say, not really good. Let's try to change something to maybe I prefer a simulation with an error in the peak, but I want to be very precise in timing, and therefore you change something. Or you change model, because, I mean, it's not given for sure that if you decided to use the linear reservoir, you can reproduce with good reliability what you're interested in. Maybe that you need to change the model, okay? And there are other features that you can look at, like the volume. If you are interested in the design of a detention basin, you are interested in the good reproduction of the volume of the hydrograph. You are not interested in the value of the peak flow, and neither the timing. What matters is the volume. Or if you want to design a dam, you are interested in both of them. Magnitude of the peak flow, because you have to size the safety discharges of the dam to make sure that even the highest flow can be vehiculated downstream. But you are also interested in the estimation of the volume, because it's the volume of the dam that you have also to size, not only the discharges. So you look at the features you are interested in and you decide. And in the past, as I said, they used visual comparison. And the procedure for trying different parameters was a trial and error procedure. So you have the linear reservoir, perfect. You have only one parameter to estimate. Let's try 10 hours for K. And then you depict this graph and you say, I am happy. Okay, 10 hours is fine. Or you see that, no, I'm not happy. So let's try 15 hours. And in doing these different trials, they used to understand what the model does, and from each trial to learn for the next one. So for instance, in the linear reservoir, if you use a large K, we already discussed what happens. The timing is anticipated. The catchment with the lower K responds more quickly. And you understand, with the lower K, the peak is higher because there is less storage. So if they tried a K of 10 hours and saw that the peak was too high, they adjusted K to a higher value. Because from each trial, they learned from the next one. And in order to learn, you have to know the model. So you have to understand what is the effect of increasing K in the linear reservoir rather than decreasing it. So it was extremely important for the first modelers to know whatever is the process. You make a climate model. It was extremely important for the modelers to understand what happens if you increase the CO2 emissions. Because if they wanted to find the correct value of the parameters with a trial and error procedure, they necessarily had to understand that. Because you understand that this takes time. And if you start making attempts just by chance, random attempts, it may take years before you get to the final value of the results, the final value of the parameters, before you get a good model. So they necessarily had to understand what's going on, how the model works, and learn from each attempt. This is why also they looked for simple models, because you understand, if you have only one parameter to change, it becomes easy. But if you have a model with 10 parameters, then understanding what happens if you increase the first one and decrease the second and increase the third, it is more complicated. And the number of attempts that you have to make increases. It was really time consuming, even with the 3 parameters with respect to one, was really a long process. Okay, but this is the trial and error procedure, and which was used up to like 1985, 1990 in most of the cases. They still used, because personal computers were not available, they still used the trial and error procedure. And then it's clear that once that computers became available, people started thinking, can I make it automatic? You know, it was the beginning of artificial intelligence, because artificial intelligence is now seen as a new term, but actually artificial intelligence started when computers became available. So it started artificial intelligence already in 1960s, in the 1960s, 1970s. And the professors that I had at the university, they started working in IBM in 1972, in Italy, in IBM in Pisa, and they started with artificial intelligence. They had the cards with the holes and to put into the PCs, and the computation may take weeks. The computation that we now make in a few seconds, it took weeks to them. So still they had to use very simple models, but this is the beginning of artificial intelligence. And of course, in the 1990, 92, there was a huge step change, because personal computers became available at home. And this was a huge step change. And therefore, of course, people wondered, can I make it automatic? The trial and error procedure, can I make it automatic? And today it's automatic. It's fully automatic. And there was a decade of research activities starting from 1990 to the 2000s, focusing on this specific problem: automatic calibration of models of whatever industrial processes, environment. And of course, in hydrology, there was this branch of research, automatic calibration of Ruoff models. And now it's very easy. You can calibrate into R. We will see how to do that. It's extremely easy and takes a limited time. there is a drawback. The drawback is that you don't need to understand anymore what a model does. And therefore, it happens quite frequently also in science that people use model without understanding what they do. And this is a risk. This is a risk, especially with technical applications. In the past, they were forced to understand the model, to understand the principle, and in a way to check reliability. Now, it's not necessarily needed. You can apply in a model in whatever. I mean, today there is machine learning. It's very easy. You can go to ChatGPT and write, how can I make a machine learning model for producing the Reno River flow in Bologna? And ChatGPT suggests to you the data to use and the codes to use in R or whatever, in MATLAB, and you can run the computation in a very limited time with a very limited learning, which is a good thing, very good thing. On the other hand, you have to be careful because this is also a risk, especially for people who work operationally. Now, when they started wondering how can I make the calibration automatic, they understood that they needed to get rid of visual assessment, of course. It is something that computer cannot do. The computer, in order to make an assessment, needs to quantify a number, needs to define a number that substitutes the visual assessment. And we can say that it is a perfect substitution. That's fine, but the computer doesn't have the capability to look and to elaborate a subjective judgment. The computer needs to elaborate an objective judgment through numbers. And therefore, they started wondering, okay, how can I find a number, a score, to say this is good? Of course, it depends on the purpose. So if you're interested in the reproduction of the peak flow, the score may be 1. If you're interested in the timing, it's another score. And so there was an interesting debate, what kind of scores I can elaborate. And they didn't use the term score, and they used, and it's still used the term objective function, because it is a function of model parameters. It is, remember, the purpose here is to estimate parameters of a given model. And therefore, the score depends on the parameters. So this is why they didn't call it score, but they called it function. And objective, because clearly it's it depends on your objective. It is the objective that you want to reach. Objective function. So what are the objective functions that they introduced at that time? First, there are millions of them, depending on the field, depending on millions of objective functions. We will see just 3 of them, but please try, given that they are very easy to be memorized and they are pillars, please remember it's a typical question quiz exam, objective functions. So what kind of objective functions do we use in hydrology? And it is very simple. First, the preliminary idea was, let's try to be very comprehensive. So what could be an objective function that in a way describes everything, that substitutes a visual comparison? So in a comprehensive way, looking at the timing, looking at the volume, looking at other features I might be interested in. And therefore, the idea was to make a comparison between each observation, to use all of them, not only the peak, not only the timing, but to use all the observations to feed the subjective function. And so the idea was, okay, let's use all the information that we have. And another idea was to find an efficient way of doing that, of comparing, of using all the observations, and of course to avoid big mistakes. And so what was the first idea was, okay, let's compute the difference between observations and simulations, all of them. Okay, so let's indicate. Let me just look at the symbols that I used on the website, because otherwise I make confusion. So I think I used X for the simulation, and okay, this was the one that was more. This is poor definition, and this is sorry, high definition. Okay, this is the one that I had to open. Okay, anyway, so this one can be closed because I have twice the same figure in the web page. Okay, so it's XT and XHAT. So let me clean the blackboard. XT is the observation, and XHAT is the simulation. And let me put on the screen. Okay, good. It's already there. So XT is observed. And of course, we refer here to implicitly to river flow, but can be everything, can be rainfall, can be CO2 emissions. And XT is simulation. Simulation is the output from the model. It can be a real-time prediction, like I want to predict river flow for tomorrow. Can be a reproduction of past river flow. I want to reproduce the river flow observed yesterday. Let's keep in a context of full generality, okay? So the idea was, let's define a quantity, epsilon t, which is the error. It's xt minus x hat. Okay, this is the error, the model error. The idea was, let's try to minimize this. I am happy when the model gives a perfect reproduction of the reality, when xt is equal to x hat t. And therefore, the idea is, let's find the parameter value that makes epsilon as low as possible, as low as possible. This was the idea. In this way, of course, and this is to be repeated for all the simulations. So the idea is, let's take the summation of epsilon t, okay, and let's find the minimum. Okay, so min. Let's minimize this. But on the other hand, we have to do it in a way, given that it's automatic, and so we cannot have a look at every trial that is performed. We have to make sure that the search is done by learning from the previous attempts and by avoiding big mistakes. Because this is the risk that you take with an automatic procedure of getting a result that is not reliable. And I give you an example to better clarify what I mean. If you minimize the summation of the errors, you may get to a situation where the summation is zero, but the individual errors are not zero. Let's suppose that you have large positive errors and large negative errors. The summation is zero, but the individual errors are large. And you have to avoid this. You have to avoid compensation of errors. So you understand that the only summation is not enough. Is it clear? I mean, it's not enough. When I pass from the individual error to a summation, I have to avoid compensation of errors. So the idea is, how can I avoid this compensation? The first idea was, let's square the errors. Let's square the errors. In this way, I remove the sign. You already understand that there might be a second solution, absolute value. We will discuss it later, okay? Let's, for now, note that the first solution that was found was squaring the error and computing the sum of the squares. And this lead to the technique called sum of squares. Or least squares. So you look for the minimum of the sum of squares. So you look for the least squares. And let's open a Google page. If you search for least squares, least square method, least squares, okay, least square method. The least squares method is a statistical procedure to find the best fit for a set of data points. Okay, Wikipedia least squares. The method of least squares is a parameter estimation method in regression analysis. Regression analysis is another way to say reproduction of with a model of something. Okay, based on minimizing the sum of squares of the residuals. The residuals is a synonym for error. Actually, there is a difference in science between residual and errors. We don't discuss this, okay? Let's consider residual here as a synonym for error. Being the difference between an observed value and the fitted value, fitted means simulated, is a synonym, provided by a model. Okay. Okay, the most important application is in data fitting. This is what we are doing, data fitting. Okay. When the problem has substantial uncertainty in the independent variable. Okay, let's see. Data fitting, here there is a nice figure, I see it. You see, look at this figure. This is a list, automatic search for the best parameter value. It's a trial and error, you see, because they start from a very poor simulation, and then they try other values of the parameter. I don't know what kind of model is this, and it's called an asymmetrical peak model. I don't know, but it doesn't matter. Here there is a parameter, and which is varied, and you see the graph of the parameter that is asymptotically converging to the best value. Okay, this is least squares. I think we can close this. And you see that what you see on the screen here, 1 second, this is precisely the summation of the squared difference between observed and simulated value. You see that the objective function is depending on theta. Theta is the parameter value. Actually, here there is one thing that it's not correct in this equation. I notice it's an imprecision. When you put in an equation independent variable on the left-hand side, the independent variable should also appear on the right-hand side. So this is not formally correct because I highlighted the dependence on the parameters of the function, objective function, but then I should find the same theta also on the right-hand side, which is there implicitly because the simulated value by the model, exact, depends not only on time, depends also on the parameter values. So I should have put dependence on theta here. Okay, and this is another thing that I should correct. Anyway, it's the equation is right, it's correct. It's just a matter of formal correctness. So the objective function is f, depends on theta, and is expressed as sum of the squared errors or residuals. Okay, this is a relationship that you should learn. Okay, and of course, if you forget the theta at the right-hand side, is fine. It's not a problem at your exam, but it's important that you learn the principle. This method is extremely important from a theoretical perspective. Why? Why? You understand one thing, if you use an objective function in this way to estimate the model parameters, as I already said, you have to make sure that it leads to a good result, a reliable result. This is not given for sure. You may use another objective function like put the absolute value there, remove the square and put the absolute value. We will do that. The next one is the sum of the absolute errors. And you get a different result in terms of parameter. In terms of parameters, you get a different result. So of course, there is a question here. What is the correct one? It's the sum of squares or the sum of the absolute values. And people did a lot of research on that. A lot. We don't focus on these details because these are details that are pertinent to statistics. It's not really relevant in engineering and in applied sciences in general. So we don't focus on these details, but at the end of the story, there are papers and books, complicated proofs that show that the sum of squares, according to some statistical assessment, is reliable under certain assumptions. And let's try to better understand from a practical point of view what reliable means. Okay, because of course we are interested in knowing that there is a theory behind, but we are mostly applied persons, technical persons, and therefore we need to understand the technical meaning of what I just said. What happens if you square an error? What happens? Okay, you remove the sign, which is important, absolutely. But besides that, what happens when you square an error? When you square an error, you give more weights to the larger errors and less weights to the minor errors. This is clear, okay? Because if you make a mistake in reproducing the river flow of 0.1 squared gets 0.01 in the summation is nothing. In this summation here or there is nothing compared to an error of 10. An error of 10 squared goes to 100. So you understand that 0.01 compared to 100, there are 4 orders of magnitude of difference. So the small error doesn't really, we don't care about it. According to this procedure, the small error, we don't care about it. The large error, we care a lot. Okay. So what is, from a technical point of view, the implication of this? It means that, when you reproduce a river flow, for instance, you reproduce a large range of values, large, from 0, because the river flow can be 0, to maybe for the Po River, 14,000. When you make a mistake over the 14,000, it's a large mistake, because even a 1% error of mistake of 14,000 is 140. When you look at the mistakes in reproducing the low flow of the Po River, which is 600, the mistake is much smaller. So if you use these squares, implicitly, you are saying that I am interested in getting a good reproduction of the peak flow. I care less of the low flow. This is the implication of using this objective function. This is the technical implication. So are we interested in predicting floods? Perfect. The least square is fine. Are we interested in predicting droughts? Droughts means low flows, means that even an error that is 0.0 something is much significant Therefore, this is not the good objective function for me. So there is a statistical implication, which is fine, that works under certain assumption, and the assumptions are actually, if you look at them, we don't look at them, but if you look at them, the assumptions are precisely what I technically said. So the assumptions are that the errors, I am interested in practical words, I am interested in the reproduction, in minimizing the large errors, not the small errors. I don't care about the small errors, which may be fine. But if we want to reproduce droughts, it's not fine. If you calibrate a model for the Po River with this objective function, you are happy with the simulation of the peak. But if you look at the low flows, no good. So in this case, indeed, you see that you may say, oh, I'm happy, the peak is fine, but look at the low flows. There is an error that is like 50% here in some of the points. So if I'm interested in water resources management during the low flow periods, this is not acceptable. A difference of 50% is not acceptable. Maybe it's not 50, but it's close to 50%. It's not acceptable. In the peak flow, the difference is maybe 0.5%, which is fine. You can see the difference here. Okay, this is the first objective function that I wanted to mention to you. And I think here there is some mention on statistical properties, consistency and unbiasedness. It's not important for me. For me, it's important is that you understand the concept. I don't care about you remembering what is consistency and unbiasedness. At the exam, you will not find any question about these technical terms. Indeed, you see that the link is not reported here. The definition is not reported here. I put the link because if you are interested in exploring more, now or later, you have the links, but what the details are not given here. Okay, let's make our break. Let's restart in 15 minutes from now. I apologize, I'm a bit late. Sorry, I had a commitment. Okay. So I would prefer at this stage to introduce the exercise, the next one, because it's an application of what we just mentioned, least squares and etc. And then I postpone to Thursday the discussion of the other objective functions. So let's then look at the next exercise. Yeah. One more thing before the exercise. Next Monday, I will open the survey, the anonymous one, for getting your opinion on the teaching. I'm really motivated. It can be compiled in physical presence or online. I'm really motivated to get the highest possible number of feedbacks. And next Monday, I will explain also how, why I'm interested and how the results are used, etc. And therefore, I will take the opportunity to highlight the importance of this survey and the value beside the importance. So please pay attention to it. It's not necessary that you are in the room. I will open and leave it open for the full day of Monday. And but please take the time to fill it, okay? And if you are attending on Monday, I will also give you some more details, but to make a summary already now, it's extremely important that you compile both the closed answer questions and the comments boxes, because I am interested in getting also your comments besides the numerical score in the closed answer questions. I think you know how the survey is structured because you should have compiled tens of them, and if you took the opportunity. So please take the opportunity and just keep in mind for now, if you are not listening on Monday to my clarification of and clarification of why the survey is important, how it should be compiled. Just keep in mind for now that it's important that you write also something in the boxes, in the text boxes, even one short sentence. You can also write, I'm super happy with this teacher, it's no problem. And but it's important that there is something written there, and I will explain you why, because this is what I value more personally. For the university, it doesn't matter. But for me, for getting your feedback, it's necessary for me to understand what are the reasons why you are critical and what are the reasons why you are happy, because this is extremely important. Okay, but next Monday, okay, May 6th. May 6th, yeah, May 6th. May 6th, yes, 1, 3, 4, yeah. Okay, let's now move to the exercise. Trend analysis. Okay, keep in mind that the trend, estimation of trend involves the application of a model. It's a linear model. Trend fitting, trend estimation, which we discussed. When you fit a straight line to a sequence of data, the straight line is a model. Okay, so parameter estimation for the straight line, same concept than parameter estimation for the linear reservoir. Okay. So let's look at this exercise, and the text is very simple, as you will see, sorry. Okay, trend analysis for a time series of daily river flows, and 1 second. Good. At the river cross section of river, mean daily river flows were observed, thus obtaining 20,000 subsequent values. Data expressed in cubic meters per second are in the text file, which is included in the zip, synthetic river flow.txt. These are synthetic river flow, means that they are not really observed. They are generated artificial data. Okay, it doesn't matter for our application. The student is kindly requested to estimate the linear trend in the time series by minimizing the sum of the squared errors, least squares. By assuming that the errors are normally distributed and independent, compute the standard deviation of the interpolation error. I will explain you later what this means, and this is not really necessary. What I'm interested in is this one, okay? And we will do it through trial and error and automatic calibration. And then in order to solve the second question, I should explain what does it mean, this assumption, normally distributed errors and independent. I don't think I will go into these details. So let's see. But again, what we do together is this. If you want to go into these details, on my webpage, there are the links, everything. So in case we don't do it together, you are much welcome to do it yourself. But again, let's focus on this. There is a text file in the zip. It is this one. I am opening it. I am working here in Windows, so it is opened in a Notepad. And you see, these are our synthetic river flows for in cubic meters per second, 20,000 values. So it's a long time series, okay? Good. And now let's look at the proposed R code. So first of all, let me save this file with the river flow data in my desktop. Okay, so let me see. Open. I open it and I save it over the desktop. Okay, desktop. Now the text file is in the desktop. Perfect. Now, let's look. There is an R code that is proposed, and let's open it. Okay, so I go back here, suggested R code, and here it is. Once again, in principle, you could do the whole exercise by copying and pasting. What we do, as usual, is cut and paste in the R console one by one. One thing, you may use RStudio. It is a bit complicated for me to use RStudio because I don't have RStudio here. I'm not allowed to install it on this PC. So let me work here in the R console, okay? Because otherwise I should connect remotely to my PC in my office, but it is a bit complicated and I don't want to dedicate much time on it. So I work on the R console. Of course, you can follow me in RStudio. It doesn't make any difference, okay? And so let me open an R console here. Here it is. R. Okay, here is the console, and let me just choose a larger character. Let's use 20. Good. And I clear the screen. So this is an R console. Perfect. Now, the data file is in the desktop. Let me see if I can set the. Let me see, set C. I don't remember the instruction for setting the working directory. Let's do this. I leave the data file in the console, or I can copy it in documents. 1 second, I think this is the best thing to do. With the File Explorer, I go to the console. Here it is. I make a copy in documents. And now it should be available in R. Okay, let's see if it is available. And I go to the website and I take the instruction for scanning the data. Okay. Because I want to make a cut and paste because I want to use the same names for the variables. So let's see if it works. Yes, it worked. Okay, because I put it in Documenti, so Documenti, it found it. Okay, let's make a plot. I'm not sure whether, let me look at the code. I'm looking if a plot instruction is there. Let me see. Yes, it is here, but I can write it. Plot river flow. Okay, type equal line. Just to see, as I said, anytime that you upload a data series, let's look at the data through a graph, because this allows you to understand what's going on, to see if there are errors, etc. This looks fine. Okay, there are no outliers. I can see some seasonality, which is fine for river flows. It's good. You may also have a look, besides the plot, at the density, probability density, because it is a useful information. Plot density. This is not in the code, but I do it anyway. River flow and type line. So just to see if it is long-tailed, if it's not, so this is the density. It is not symmetric, of course, it's river flow. The tail is moderately long. That's fine. I mean, it is looking fine. And here we can see that the max is about 8,000. Let me look at the average just to understand mean river flow, to understand what kind of river is this, okay? So it's quite a large river, and the average flow of 1,500 cubic meters per second is more or less the same average as the Po River. And let me see the max of river flow, just to see, again, what's going on. Okay, like the Po River, it's similar. And these checks that I did are finalized to my understanding, just to see, to understand what is the process I'm dealing with. And if I had also an indication of the river, like it is the Danube River, it would be good also to look in the web if there is a map of the catchment to understand the region it refers to. If it is a small creek, it would be also nice to go on Google Earth and see the shape of the catchment, if it is steep, if there are a lot of rocky components, just in order to get an idea, okay? For instance, if you knew the length of the main reach of the river, the length gives something also about the time of concentration. And so you can understand a guess of the K value. So this is information that if you work in practice, you should look for it on the web. Okay, so let me plot again the river flow, because we are supposed to look for trends. And as you can see here, there is not an easy answer to whether or not there is a trend. So indeed, in order to get a final answer, we need to make a trend estimation, and we have to fit a straight line over it, okay? And to fit a straight line, there is a ready-to-use function into R. So I could resolve the problem with just an instruction. But let's keep this easy solution for the end of the exercise. So let's wait 15 minutes. And in these 15 minutes, let me make, instead, let me use the old method. The old method is to write a model of a straight line, which involves two parameters, remember, intercept and slope. And let's use a trial and error procedure first by looking at the sum of the squared residuals as an objective function. Okay, so it is not a visual assessment of the trial and error procedure. I make an assessment through the computation of least squares. Okay, so let's move forward one step at once. Let me clear the screen. So first of all, straight line. The straight line is a model with two parameters, intercept and slope. Okay, so let's try to simplify the computation. Let's fix the intercept at a pre-assigned value, and the value is the value of the average. You may remember that the mean value Yeah, it's not really the average, so it's a little bit less than the average. But given that this is a trial and error procedure, let's try by fixing one parameter and varying the second. Okay, so this is what we do. Let's fix the intercept at 1400. So why 1400? Because let's suppose that there is an increasing trend. If there is an increasing trend, it means that the straight line should start at a lower level with respect to the average, and then the straight line should cross the average and end at the end of the time series at a level that is above average. So in fixing the intercept at a lower level with respect to the average, I am, in a way, assuming that there is an increasing trend. And now I want, for different values of the slope, to compute the sum of squares to see what is the best fitting slope. To see what is the best fitting slope. Is it clear what I would like to do? Let's see, okay, if it is clear. So let's put a trial value for the slope at b equals 0, okay? So let me copy this. So I am assuming that the straight line is horizontal, starting from a level that is below average. Let's see what is the goodness of the fit. What is the resulting sum of squares? Okay, to be compared with the next attempts, okay? So, first of all, application of the model is very simple. I mean, let me just copy this here. So I am computing a straight line. So I am approximating the river flow with a straight line. The straight line is called river flow 1. And you see that it's equivalent to intercept plus slope, which multiplies a sequence from 1 to 20,000, which is time, is progress of time. This is my computed river flow. It is an horizontal line. If you plot it, it's an horizontal line. And so if you compare it with the observed river flow, we can make here lines river flow, call equal blue, just to make a difference. And this is the comparison. Of course, I should have done the opposite. First, plot river flow. Okay, and then lines river flow 1, because otherwise the scale is reduced. So this is the good plot. So this is the straight line that I'm trying. I am trying this straight line, which I don't know, maybe good, maybe poor. Let's compute the sum of the squared residuals. Of course, the best straight line is the one with the smallest sum of squared errors. Okay, so in order to check whether this is good or not, I need to compute the sum of the squared errors. Let's do that. Okay, so I get in the code here. This is actually the root of the sum of squares, what I am computing. Let me compute first the sum of squares, this one. So let me copy it and just print it over the screen. You see the number is much large because given that I have large errors, squared, it's very large. So for the sake of keeping it in memory, it may be advisable to compute the square root of it because it's a number that is not as large, you know. So the square root is like 134 thousandths. Let's keep it in mind. So let's call it SQRT1. Okay, this is the first trial, and this is the square root of the sum of square, SQRT1. Okay, 134 thousandths. Now let me try with another value. And the other value may be, let's keep the slope to equal to 0, but let's try with an intercept that is equivalent to the average. What is your guess? The sum of the squares will be lower or higher? You should be able to provide an answer, but while you think at it, I'm making the computation. So let me just clear the screen. And let me go to the instruction where I fixed the intercept. And instead of putting this value, let's put mean river flow. I'm not sure whether in the code this is done. And no matter if it's done there or not, I want to try it, okay? So this is my intercept. Now let me compute once again the river flow one, okay? Here it is. Again, slope is 0, but the intercept is equivalent to the average. Let me compute SQRT1, sorry, 2, to be compared with the previous one. So SQRT1 was this number, SQRT2 is this number. It's lower, not much lower, but it's lower. This is what I was expecting, because if you interpolate a whatever time series with a slope 0, the best value that you can give for the intercept is the average. This is what I was expecting. Now, the question could be, what happens if I try with a slope that is different? Let's try with an increasing slope. Okay, so what I can do now is I keep the intercept equal to the average. Let me put B 0.1. I think this is too much. Let's see if it is too much or not, okay? Now I can compute river flow 1 again. And then SQRT 3. Okay. Now let's see what happened. SQRT 2 was this value. Let's see if we worsened or improved. If it is worsened or improved, SQRT 3. It's much larger. No way, it's too much. Let's look at a plot to see if indeed it's too much. So let's plot once again. Our plot is still here, correct? Let me show. Let me show another line with the color blue. You see, it's too steep. No, it's definitely not good. So this was B 0.1. Let's try with B 0.01. This is trial and error. This is what people was doing up to 30 years ago, okay? Because there was no automatic procedure, nothing. And therefore they were just trying to see what was going on. And through the visual comparison, the visual comparison is what I'm doing here, okay? So let's try once again, clear the screen, and let me go to 0.01. Okay, good. River flow 1 again, and then SQRT 4. Good. So SQRT2 was this one is the best that I have for now, and 4 is it's not so bad. It's comparable. It's a bit maybe that if we try to lower the intercept a little bit. So let's take the previous value of the intercept. Because when you put an increasing trend, as I said, you need to make an intercept at 0 that is lower than the average. So let me try with the previous value of the intercept. It was like, here it is. So let's compute again river flow 1, and then SQRT 5. So let's see, SQRT 5. You see, this is the best value that I found so far. So it seems that there is an increasing trend. And of course, it's not given for sure that if you have a good reason for laughing, let me know, so I can also join you. I think there might be indeed good reasons, and it's not granted for sure that this is the best one. So I could try to make other small changes to see what happens, but I think at this stage we have only 10 minutes left. I think we should now turn to modern time. So for sure, there must be into R an automatic procedure for calibrating a model, given that we use the objective function sum of squares. So let's take with very few instructions this automatic procedure. And first, let me prepare it. Clear the screen, and I go here. Sorry. Here I have to go. And here you see that indeed there is the attempt with another value of the slope. And here there is another attempt with the slope 0.02. Now let's turn into the automatic procedure. In order to make the procedure automatic, I need R to get the means to compute the sum of square with just an instruction, with a function. And the function is this one. Okay, so it is a function that, depending on the value of the slope, so only one parameter is changed, depending on the value of the slope, returns the sum of squares. And it is a function that is repeating the computation of river flow 1, but I need to condense this computation in just one function. So I need to give this function as input to R. Okay, so let me go here. I just make a cut and paste, and this is the function. Basically, if you now write the name of the function, sorry. Oh, sorry. Why? Sum SQ. Here it is. You see the function here. Okay. So this means that if I say sum SQ of 0.01, I should find the same value that I found previously. Fine. And now I can try 0.02, and you see that is larger. I could try 0.09. It's a bit lower. So you see that through a function, now I make the computation faster. I made the computation faster. We already tried to learn how to write functions into R, and this is very simple. Okay, now we can use an automatic procedure, which is included into R, to find the best value of the parameter B. So far, I understood that 0.009 is the best value, but let's try to explore more, to make more trials. These automatic procedures are conceived in a way that they learn from the previous attempt, and therefore their search is a guided search. There is a lot of research behind this, and we don't know to be informed about these details, how they work. The important thing is that we check at the end of the story if the result is reliable. Okay. So let me clear the screen and let me now run this automatic optimization. It's just an instructions. It's just an instruction. Let me just copy it and paste it here. So you see, I use the optimize function. The optimize function is embedded into R. It is only one possibility. There are tens of them into R. Some of them are most indicated when you have more than one parameter to estimate, whatever, but there are several of them. And this is one that is ready to use, and you have to give as an argument the name of the function to be minimized, sum SQ in this case, the function that I just wrote, and you have to give the search interval. So I am telling the function to search in the range of slopes minus 0.5, 0.5. It is larger than what is strictly needed, but better to give a large interval. And you see, that's it. So if I now plot the results, this is the minimum slope, 0.00787, and this is the objective function, resulting objective function. This is automatic calibration according to the sum of squares. So you see that indeed it's very quick. In order to do that, I had to write the function SUMSQ, okay, the one that you see here. Okay, so in the same way, you could write here the linear reservoir. If I want to express the river flow, simulate the river flow depending on precipitation, I could write here the function of the linear reservoir. We have an exercise later on where we indeed write the function of the linear reservoir, which is very easy because it is a numerical computation. So in this procedure, we have the liberty of using whatever function to minimize we want. And in this case, we use that of the linear model. But given that the linear model is extremely popular, we have also a prepared function into R for fitting data with a linear model. And it is this function here, LSFit. It means LSFit means straight line fit. This is the function, and let me copy it and then I explain to you the arguments. So what we are telling R here is to fit a straight line to river flow, which is depending on time, and time is the first argument, sequence from 1 to 20,000. You see, very quick. And let's see what is the result. And it is a list, the result, and let's look just at the parameters. And these are the parameters. So basically, what you see is that the best parameter is 0.00562223. This is the best parameter for the slope. And you have also the best parameter for the intercept, because this function of R estimates both of them at the same time, intercept and slope. And the intercept is a little bit more than 1485 that I fixed before. This explains to you why the resulting best slope is different. It's a bit lower in the case of the estimation at the same time of intercept and slope. Okay. Now, one thing that I could do in order to check the result is to set the intercept at this value, 15, 15. So let me go back and let me fix A at 15, 15, which is the result from the list from the straight line estimation. Now, if I repeat then the estimation with this instruction here, I should get the same result that I got from for the slope from the straight line fit. So let me try here, and let me see PR1. You see, I got the same result, which means this is, of course, what I was expecting. So with the very simple case of a straight line estimation, we applied the least squares algorithm so far for estimating only one parameter, the slope of a model that is simply given by a straight line. But of course, this sets the basis for applying it for the estimation of the linear reservoir. Of course, I need rainfall data, which I still don't have here, but the next exercise will be precisely a linear reservoir estimation. By the way, this optimize function, you can use it even if you have more than one parameter. It's no problem. I think for today we can stop here. Do you have any question, clarification, whatever? Yeah, please. LSFit is actually a regression method. So it's linear regression. It's application of linear regression. And so LSFit estimates both intercept and slope. Optimize is a function that looks for a minimum of a function, which is in this case some skew that you have to write. And in this case, I gave as function some skew the straight line estimation. So I am expected to get the same results, with the exception that I estimated only the slope, not the intercept. But if I give as intercept value in my sum of squares function the correct value, I am expecting that optimize and LSFit give the same result. The difference is LSFit is just for linear regression. Optimizes whatever function that you define. Was I clear? Okay, thank you. Because, I want to make sure that I was clear. Other questions? No questions? Good. So see you on Thursday online. Grazie. Thank you very much.